simply supported beam or supported by a spring. It shows the magnitudes of oscillations due to free and forced vibrations in simple structures and how damping affects their vibrations. Students may vibrate the systems manually. They may also force the vibrations using a high-quality variable speed servo motor driving a rotating offset mass forming an exciter. The VDAS Mark II software includes functions to display live plots of first and second derivatives, to show velocity, and acceleration waveforms based on the displacement signal. A digital display shows the motor speeds in units of frequency in Hertz, radians per second, and revolutions per minute. The TM1016 is manufactured in line with the latest European safety standards. The unit includes a dashpot damper for use with a non-toxic fluid of stable viscosity. The TM1016 allows students to use Rayleigh's approximation to predict vibration frequency and also to find the beam-only frequency using Dunkerley's method. Further experiments can be conducted on the TM1016. Additional mass can be added to the beam. An undamped vibration absorber is also included with the unit. This demonstrates the typical behavior of a 2-degree of freedom system. Students learn how to tune the vibration absorber to eliminate the oscillations of the main beam. Acceleration is measured with the integral accelerometer. A non-contacting sensor measures beam displacement. The sensor has no physical contact with the oscillating system, so it has no damping effect.
Welcome to my YouTube channel Kadam Academy. Dear friend, under the single degree of freedom, we have covered the undamped, damped, force vibration, and in this mechanical vibration series, today we are going to study this example on the force damped vibration. Under this force damped vibration, I will read the numerical. When a free vibration test is run on the following system. This is the system. The ratio of the amplitudes on the successive cycles is 2.5 to 1. Determine the response of the machine due to rotating unbalance. See, here is the rotating unbalance we are going to study of magnitude 0.25 kg meter. This is rotating mass with the distance. So due to this, what will happen? Unbalance in the magnitude, that is 0.25 kg meter. When the machine operates at 2000 rpm revolution per minute and damping is assumed to be viscous. So friend, what will happen here? What is the given here? The all were ready, and value of E also given, elasticity also given, the 4.5 10 raised to minus 6 m raised to 4. So value of m 125, it is given in this figure at the distance of 80 centimeter. Friend, what will happen here? What we have to do? We have to find out the response of the machine due to the rotating unbalance. That means what we have to find out? We have to find out the x for this due to this machine. Here is the combination of these two. The viscous we have to assume viscous damping as a cantilever beam. So cantilever beam as a viscous damping we have to assume, and we have to solve it for that numerical. So I will show you as this is the transverse vibration is there due to load P and due to the rotating force. Okay, this that P amount is the, I will calculate. See here, what is the given data? As there is the harmonic force, it will rotate from this cycle. This is the amplitude x1, x2. The ratio is given to us. What is that ratio? x1 by x2, 2.5 to 1. 2.5 to 1. It is given in the numerical. Okay, so 2.5 to 1. So this ratio is 2.5. And this MOE is given to us. MO is the 0.25 kg meter. Omega, we have to find out the frequency due to this force applied on this system. So what is the frequency? By using this revolution per minute, 2000 into 2 pi by 60, you can calculate 209.44 radian per second. and this value of E, I and M also given in the numerical. So what is the next step? So what we have to find out? We have to find out the response in the system, response of machine. What? Response of machine due to what? Due to rotating. Condition was rotating unbalance. Okay, so this response you can find out by using this equation, small x sine of omega t minus phi. So this is the equation to find out this response. From this equation we can find out, but in this case what we have to ask, the response means we have to find out the x. Okay, how to find out this x amplitude? By using this formula, x is equal to x upon MOE by capital M, which is equal to r square upon under root of 1 minus r square bracket square plus twice zeta r square under root, and this is the bracket square. So in this case we don't know the values. Here we have to find out the x. Okay, what we have to find out? We have to find out here x, and this M capital M is given, r we don't know. To find out these values, the r is equal to what? R we can find out by omega n. Omega we know, omega n we don't know. How to find out the omega n? To find out the omega n, which is equal to under root of k by m. M for this system. M is given, we know the value of m is 125. K we don't know. So as this k, nothing but this cantilever beam. This is the k for this cantilever beam. We have to find out. How to find out this? That formula by using this P upon T. Okay, the deflection. This deflection for this cantilever beam, for the square dimension, is given to you length, that I will write the formula PL cube by 3EI. From this you can find out this K, P upon del, this P upon PL cube upon 3EI. That means what? K is equal to, I can write from this 3EI upon PL cube. The real value of L is given to us, known to us, that L is 0.8 meter in this 80 centimeter. Okay. So if we put these values here, what will get? Value of K is 5.27 10 to 6 Newton per meter. Now next step we'll go for the K. Once we got the value of K, this K we know, we can find out the value of omega. How to find the omega? Omega n we have to find out. Omega already we have calculated. Omega we can find out by using this K by m under root of K by m. We know the value of K, we know the value of m. The system 5.27 into 10 to 6 upon 125. Then omega n becomes, using this calculator we will write 2.50396 radian per second. This is the value for omega n now. Once you find out the omega n, you can find out the value of r. So R now you can find out omega by omega n. So R becomes 209.44. Already we have calculated the value of omega by using this 2000 RPM. Okay, and this 205.0396, which is equal to 1.02. This is the value of R. Okay. Now next step, what we have to find out? Once we got the value of R here, okay, so we have to find out the final, our aim destination is find out the X. But in that formula, see here, this is the formula for the X. This amplitude we can find out by using this formula, X upon MOE by M R square upon this under root of 1 minus R square bracket square plus 2 zeta R bracket square. R we know in this case, this calculator MOE we know, M know, but zeta we don't know. To calculate this zeta damping ratio, we'll see how to find out the value of zeta. Here, the zeta we can find out the value of this x1 by x2 ratio is given to us 2.5. Okay, logarithmic decrement by using this logarithmic decrement delta, which is equal to 1 by n log to the base x1 by x2. Okay, 2 pi zeta upon under root of 1 minus zeta square. So this is the formula for this logarithmic decrement. Okay, so delta. So this delta, this n is in this case only one cycle. X1 by x2 is 2.5. So we can write like this: 2.5 is equal to 2 into 5 zeta upon root of 1 minus zeta square. Squaring on both the sides, we can write like this also: ln 2.5 circle bracket root of 1 minus zeta square 2 pi zeta. In this, just solving this one, what will the just squaring on both the sides, 1 minus zeta square is equal to 6.86 zeta square. Lastly, what will happen? This will write here 1 minus zeta square is equal to 47.2 zeta square. So this 48.2 zeta square is equal to 1 zeta now become 0.144. This is the damping ratio. This is the damping ratio for this system, 0.144. Once we know the value of damping ratio, we can find out the, by using this numerical, the value of the this formula for the X. So what we have to find out? X we have to find out by using this formula. In this case, X upon MOE. MOE already known to us for this system. MOE is 0.25 upon 125, which is equal to this R square. R square already we have calculated here. That is the value of R 1.02. The value of 1.02 square upon under root of 1 minus 1.02 each square bracket square plus twice zeta. Zeta already just we have calculated the value of zeta is 0.144 into 1.02 and this extended bracket square, the square root. Okay, after solving this, value of this X, right here value of X is 7.02 into 10 raised to minus 3 meter. Now again we have to write in terms of the millimeter, 7.02. So friend, this is the response of this system What is this? This is the response for the system is 7.02 for this condition. Here is the rotating condition. So friend, for more and more updated video, please subscribe my channel. Thank you very much for watching my video.